Number 12. Gravity is not actually a force at all, and Einstein proved it, but nobody has ever explained why bending fabric would make objects fall. In 1915, Albert Einstein published his general theory of relativity, arguing that gravity is not a pulling force between objects, but the result of massive objects curving the fabric of space-time itself, causing other objects to simply follow that curved path. This replaced Isaac Newton's 1687 model of gravity as an invisible, attractive force acting instantly across any distance, a concept Newton himself admitted he found deeply unsatisfying and could not physically explain. Einstein's geometric explanation matches every experiment ever performed, yet it still doesn't answer the deeper question: why does mass bend space-time at all? Nobody has ever identified the actual mechanism. Number 11. Physicists have never detected the particle that is supposed to carry gravity, despite searching for it for nearly a century. Quantum mechanics explains 3 of the 4 fundamental forces using particles: photons for electromagnetism, gluons for the strong force, and bosons for the weak force, each one experimentally confirmed inside particle accelerators like CERN's Large Hadron Collider. Gravity is theorized to have its own force-carrying particle, called the graviton, first proposed in the 1930s. It would need to be massless and travel at light speed to match observed gravitational behavior. As of 2026, no experiment has ever detected a graviton. Physicist Freeman Dyson argued in 2013 that a graviton may be fundamentally undetectable using any technology humans could ever realistically build. Calculations suggesting a working detector would need to be larger than Jupiter itself. Number 10. Gravity is roughly 10,000 trillion times weaker than the other forces of nature, and nobody knows why. This is called the hierarchy problem, formally identified by physicists in the 1970s. A small magnet can lift a paperclip against the gravitational pull of the entire planet Earth, demonstrating just how astonishingly weak gravity actually is compared to electromagnetism. Theoretical physicist Lisa Randall at Harvard proposed in 1999, alongside Raman Sundram, that gravity might be leaking into hidden extra dimensions we cannot perceive, diluting its strength in our own three-dimensional world. No extra dimensions have ever been confirmed. The Large Hadron Collider searched specifically for evidence of them starting in 2010, and found nothing. Gravity's extreme weakness remains one of the least explained numbers in all of physics. Number 9. In 1933, an astronomer calculated that galaxies should fly apart based on the gravity of visible matter alone, and nearly a century later, we still don't know what's holding them together. Astronomer Fritz Zwicky at Caltech studied the Coma Galaxy Cluster and found its galaxies were moving far too fast to be held together by the gravity of visible stars alone, unless significant unseen mass was present. In 1978, astronomer Vera Rubin confirmed this using the Kitt Peak National Observatory, showing that stars at the edges of spiral galaxies orbit at nearly the same speed as stars near the center, defying Newtonian predictions entirely. This invisible mass was named dark matter. It appears to outweigh visible matter roughly 5 to 1 across the universe, and despite decades of searching using detectors buried underground, no dark matter particle has ever been directly detected. Number 8. In 1998, astronomers discovered that gravity itself appears to be losing a cosmic tug-of-war against an invisible force pushing the entire universe apart faster and faster. 2 independent research teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees, studied distant exploding stars called supernovae and found the universe's expansion was accelerating, not slowing down as gravity should cause. This discovery, which earned all 3 astronomers the 2011 Nobel Prize in Physics, implied the existence of dark energy, a mysterious force making up roughly 68% of the entire universe. Nobody knows what dark energy actually is. It behaves like a form of negative gravity, and current physics has no accepted explanation for why it exists, or why it wasn't strong enough to prevent galaxies from ever forming in the first place. Number 7. 2 NASA spacecraft launched in the 1970s slowed down slightly more than gravity alone should have allowed, and for decades, nobody could explain why. The Pioneer 10 and Pioneer 11 spacecraft, launched in 1972 and 1973, were tracked precisely as they left our solar system, and physicists noticed both were decelerating slightly faster than the sun's gravity should have caused, a discrepancy first formally reported in 1998 by physicist John Anderson at NASA's Jet Propulsion Laboratory. The Pioneer Anomaly Anomaly sparked genuine speculation that our understanding of gravity itself might be incomplete at extremely large distances. In 2012, a team led by Slava Turishev at JPL finally determined the cause was thermal radiation, heat escaping unevenly from the spacecraft's own power systems, creating a tiny amount of thrust. The mystery was solved, but only after 14 years of physicists genuinely questioning whether gravity behaved differently far from the Sun. Number 6. Several NASA spacecraft passing by Earth for a gravity assist gained or lost tiny amounts of speed that our equations say should be completely impossible. Beginning with the Galileo spacecraft in 1990, engineers repeatedly noticed that spacecraft performing flybys of Earth to gain speed using its gravity emerged from the maneuver with slightly different velocities than predicted, a pattern documented by physicist John Anderson in a 2008 paper. This became known as the Flyby Anomaly. The discrepancies were extremely small, just millimeters per second, but consistently unexplained by standard orbital mechanics, appearing across missions including Near Shoemaker in 1998 and Rosetta in 2005 and 2007. No confirmed explanation has ever been established. Some anomalies have since disappeared with improved measurement techniques, but researchers have never fully closed the case, leaving open the unsettling possibility that our gravitational models are missing something subtle at planetary scales. Number 5. An alternative theory suggests dark matter might not exist at all, and that gravity itself might simply behave differently than Newton ever imagined at galactic distances. In 1983, physicist Mordechai Milgram in Israel proposed modified Newtonian dynamics, or MOND, arguing that Newton's law of gravity subtly breaks down at extremely low accelerations, exactly the conditions found at the outer edges of galaxies, removing the need for invisible dark matter entirely. MOND successfully predicts galaxy rotation curves without dark matter in many cases, a genuine achievement that dark matter models sometimes struggle to match precisely. But MOND fails to explain gravitational lensing patterns observed in colliding galaxy clusters, like the Bullet Cluster, studied by astronomer Douglas Clow in 2006. 40 years later, physicists remain split, unable to conclusively prove whether dark matter is real or whether gravity itself is fundamentally different than Einstein and Newton believed. Number 4. Gravitational waves, ripples in spacetime predicted by Einstein in 1916, were not directly detected until a full century later, and they revealed we'd been missing an entire category of cosmic events. On September 14, 2015, the LIGO observatory detected gravitational waves for the first time, produced by two black holes colliding 1.3 billion light-years away, confirmed by physicist Rainer Weiss, Barry Barish, and Kip Thorne, who won the 2017 Nobel Prize in Physics for the discovery. The signal lasted only 0.2 of a second, and it required detecting a distortion in spacetime smaller than 1/10,000th the width of a proton. Since then, dozens of gravitational wave events have been confirmed, including the neutron star collision GW170-8117 in 2017. Scientists now believe the universe is filled with a constant, invisible hum of gravitational waves from ancient collisions, an entire hidden layer of cosmic history that remained completely undetectable until 2015. Number 3. Inside every black hole, gravity becomes so extreme that the equations of physics simply stop producing meaningful answers, and nobody knows what actually happens there. At the center of a black hole lies a theoretical point called a singularity, where gravity becomes infinite, and the fabric of spacetime, according to general relativity, is crushed down into a single point of zero size. Physicist Roger Penrose proved mathematically in 1965 that singularities are an unavoidable consequence of general relativity, work that earned him the 2020 Nobel Prize in Physics, but the theory itself breaks down at that exact point. General relativity and quantum mechanics simply cannot agree on what happens inside a singularity. Some physicists propose the true center is not infinitely small at all, but something else entirely that current physics has no equations to describe. Number 2. Gravity is the only fundamental force in the universe that physicists have never successfully combined with quantum mechanics, despite nearly a century of trying. Every other force in nature, electromagnetism, and the strong and weak nuclear forces, has been successfully described using quantum field theory, confirmed repeatedly through experiments at facilities like CERN since the 1970s. Gravity refuses to fit. Attempts to unify it with quantum mechanics produce mathematical infinities that cannot cannot be resolved, a problem physicist Richard Feynman openly acknowledged in lectures throughout the 1960s while attempting his own approach to quantum gravity. Modern efforts, including string theory, developed since the 1970s by physicists including Leonard Susskind, and loop quantum gravity, developed since the 1980s by physicists including Carlo Rovelli, both attempt to solve this problem, and neither has been experimentally confirmed. Gravity remains the one force science cannot yet fold into its most successful framework. Number 1. If gravity had been even slightly stronger or weaker at the moment of the Big Bang, nothing in the universe, including you, would exist, and nobody can explain why it was set so precisely. Physicists have calculated that if the strength of gravity relative to electromagnetism had differed by roughly 1 part in 10 to the 40th power, stars would never have formed correctly, and galaxies, planets, and life would be entirely impossible. Physicist Martin Rees at Cambridge documented this in his 1999 book, Just 6 Numbers, describing gravity's precise value as one of several fundamental constants that appear finely tuned for a universe capable of producing complexity. No known law of physics requires gravity to have this exact value. Some physicists point to a multiverse of random universes as an explanation. Others admit we simply do not know why the force holding galaxies together, and holding your own feet to the ground right now, happens to be tuned with a precision that borders on the impossible. If you want to see more videos like this, click the video on screen now, and make sure to subscribe.